Now, in this example, what we need to do is we need to model two scenarios, both concerning fallen objects. And we need to try and use the models to determine the height at which the objects are thrown from. So, here's the question. It says, Galileo is playing around with stones again. He drops one stone from a tower, and then 1 second later, he decides to throw another stone downwards with a speed of 12 meters per second. Both stones reach the ground simultaneously, so we're supposed to find the height of the tower. Okay, so if I just highlight some information that we need. So what we know is, in one case, he drops the stone from the tower, and then a second later, he throws. Now this is something different because he gives the second stone, some speed initially. And then we also know that these things hit the ground simultaneously. And using these three, we're going to try and work out exactly what the height of the tower is. Okay, so you can see that in my diagram, I have the picture all set up. This is the man himself, Galileo, and actually in his experiments, in his research on the effects of gravity, this was actually one of the things he used to do. He used to go to the Tower of Pisa and run experiments understanding how gravity influenced the motion of objects. Whether or not he did this particular experiment is, well, I don't know, a mystery to me, but seems like a good question to ask. So you can see that in my diagram, I've set up reference system. And it's chosen so that y points downwards for convenience, for our sake. And this is the goal: find the height of the tower H. Okay. So, and this is meant to be my leaning Tower of Pisa. So this is Tower of Pisa, which I believe wasn't leaning so much back in the 16th century. Okay, so what we need to do, so let's have a look at the first stone. Now what you'll see is I might skip some steps. This is stone 1. It's falling vertically downward due to the action, as we know. Now let's just keep this in mind. Keep this in mind that this is there. Okay, so the origin is at the top of the tower where Galileo is releasing the stone. The stone's moving vertically downwards, so let me just put this, moves vertically down. Again, notice that we don't know the mass of the stone, but we know from doing a variety of examples so far that the force that acts on this is the gravitational force. We know the magnitude of this force, mag, I'll write for short, mag is mg. And this vector, this is our vector to represent the force. This vector points downwards in the positive y direction, so we can immediately say that, okay, this stone is experiencing a force that can be described by the following vector, mgj. Okay, now, actually what I'm going to do is I'm going to skip some steps now, because you can repeat a lot of this if you if you look back at the old videos. So just a few essential pieces of information for stone 1. So it says that the stone is dropped. Stone 1 is dropped in the question. So this implies that V y. Now Vy is the vertical component of the velocity for this stone, but I'll put 1 as a superscript to tell you that it's stone 1. So initially this speed is 0. Okay, now let me just clear this up. So this is velocity, vertical velocity. For stone 1 initially. In addition, remember the displacement, the start of our reference system coincides with where Galileo drops the stone. So y, the displacement for this is y1 of 0, 1 being the stone 1. And of course we have this simply because this is where the stones drop from. So these are your initial conditions. So I'll put IC. ICs usually people write. So these are your ICs, and Newton's equation of motion is written F, usual stuff, dV. Now I'll put 1. Actually, you know what? Let's mark this force with 1, just to note that we're dealing with the stone 1. So we have F equals this. V1 is equal to Vy of 1 of t with j as the coefficient, the basis vector, the unit vector j. Now, of course, skipping steps, we derive this equation. And you should verify this for yourself. We derive this equation. Okay, and in addition, I'm now going to skip even more steps. Simply integrating this equation once gets you you can find what the vertical velocity is using the initial condition, so you don't have to worry about having any unknown constants. So you have gt for this, and then remember that y is linked to Vy, y1 is linked to Vy1 via the derivative with respect to time, so one can show that this is the expression. Okay, so notice that these things don't contain constant terms, because what's happening is once we have the indefinite integration step, we then apply the 0 initial conditions, and this kills the constants. Okay, so this is what we have in this case, if I'm not wrong. Right, now stone 2, well, by the way, m is the mass in this one, mass of stone. Didn't matter actually, doesn't really matter, because as you can see, the mass just goes out, literally out the equation. Now I'm going to copy this because a lot of this is just routine deductions based on what we've already done. Copy. Okay. Except this time what I'll do is I'll make the stone a little larger just for illustration. You know, it doesn't really matter what the size of this stone was or is. Well, it's like a boulder now, but anyway, good. So this is also moving vertically downwards. So we know that in this case, the mass, we're going to call capital M, just for the sake of simplicity, mass of stone 2. And in this case, the gravitational force as magnitude capital Mg. And then our force experienced by this is capital Mgj. Now, the SI calculation. We're going to set the problem up for stone 2. And this is going to be slightly different. So let me just put this across. So what's the initial conditions? Remember, well, just like last time, they're being dropped from the same height. Remember that the position that stone 2 is dropped from is the same as stone 1. So the displacement of the stone at t equals 0 is 0. Okay, so here, by the way, maybe I should just make a note at the bottom. So yj is displacement vertically of stone j. J equals 1, 2. Now, what about the initial condition for the velocity? Well, he does something different this time with this stone, and he gives it some initial velocity. So what we can say is Vy of 2, the velocity of stone 2, when t is 0, is 12 meters per second, okay, or just 12 in this case. And following above steps, what we get is dv. You'll do exactly the same stuff. dv2 by dt equals g. Okay, and this is for us now to handle, because something slightly different happens in this case. So, by the way, everything we do here is valid. You know what? This isn't really 0. This is actually 1. Makes no sense. This was exactly the point I was going to make next. So initially, it's not 0 for this stone. Initial time is t equals 1. Okay, this is very important. Why? So what we're doing here is valid for t greater than or equal to 1. Initial conditions correspond to t equals 1 when stone is thrown. Great. Now, we're going to go on to solve this problem. So what have we got? We've got two initial conditions that are now set at a delayed time. And you'll see that I do some nice, or if you like, some tricks that help simplify the problem a bit, because it can get a bit messy. And what we'll do is we'll use this differential equation. We'll use this differential equation. Okay, and with these initial conditions, hang on, there we go. So we have this, and this comes later. So, stone 2. Now, have a look what we do. So, usual step, integrate with respect to t. What do you get? Well, you get Vy of 2 equals the integral of g with respect to t, which is equal to gt, of course, plus some constant. Now, what about this constant? Well, now I'll use the IC, the initial condition on the velocity, which is taken from t equals 1. So, what do we get? Well, this, we just have to sub in 1. So we have this on one side, because that's our condition. And then on the other side, we're using this expression. So we have g times 1, because we just substitute t equals 1 in. C. So this implies that c equals 12 minus g. After this, this gives us that V2 is this. It is GT plus 12 minus G, which simplifies to, get rid of this, simplifies to GT minus 1 plus 12. Now, clearly, from this representation, this second one, that I mark with a really heavy star there, fat star. So clearly this has satisfies the initial condition. If I put t equals 1, you can see that automatically the velocity at t equals 1 drops out as 12, which is good news. I can also differentiate star with respect to t, and I can get the equation that we started with, which is dvy 2 by dt equals g. So what can I do next? Well, what I'm interested in is what is the displacement, and then in a bit it starts to get a little messy. y2 of 1, y2 of t. Well, for this I just have to integrate star with respect to t. Now watch what I do. You can do this by brute force, it's entirely up to you, or you can do what I'm about to do, which is something that we've practiced a few times, and I'll explain why I do this in a second. So I'm going to integrate star with respect to t. So I have integral v2 or vy2 should give me y2 of t, and then I have this integral to do. Now personally, here's where the taste for the preferred type of integration comes in. This is going to be an indefinite integral. I see that, you know, this stone got dropped a second later, and that information's actually embedded in this t minus 1. So when you put t equals to 1, this factor immediately drops out, and what you end up with is you end up with your initial values. I like to keep things that way, so when I integrate, and what I won't be doing is this gt squared over 2 minus t plus 12 plus 12t, plus c, c's a bad choice, plus b. I'm not going to do that. What I'm going to do is things that we've done before when we look at, say, trajectories traced by solutions of systems of differential equations. So what I'm going to do is I'm going to pretend that I have the substitution that u is t minus 1, and then carry out this integral using this substitution. So in the end, what I end up with is the following. I end up with g over 2 t minus 1 square plus 12 t plus b. Okay, so you can see that I've integrated the first term so that I preserve the fact that I have a term that just vanishes when t is 1. And this keeps the algebra for me a little less cumbersome for this question. Okay, what about b now? By the way, it's absolutely your choice what you want to do. You can, if you want, if you're a sucker for hard work, you can grind this out and do exactly what I said I wasn't going to do, and you just end up with the same answer. But, you know, in this problem, it's better to just keep things simple, I think, because then some of the stuff gets a bit messy later. So what about b? Well, I'm going to now bring in the initial condition, because without these, arbitrary constants are pretty much difficult to determine, if not impossible. So use this. So what have we got? We've got y2 of 1. Now you can see I'm going to make a substitution of 1, which kills this term here, and with the curly brace underneath. So I know this is, by my initial condition, 12. I know this is this, but simultaneously I have g over 2 multiplied by 0 squared plus 12 times 1 plus b. And what you can see is this immediately gives you b equals minus 12. So now the updated form for y of t is as follows. And this is for me ideal for what we're trying to do. So you can see that now the factor which vanishes is in both terms here, 1, 2. And when t is 1, these factors immediately vanish. Now, you could have done this without doing what I have done. You could have grinded this out. And what you could then do is make your solution look like mine by completing the square and so on and so forth. Okay. So, we have to find the height of the tower. That's the end message. We have to find height of tower, h. Okay, we were told the stones land on the ground at same time, say, let's call it capital T. You know I like to use this notation. Okay, so effectively at capital T, at T equals capital T, because they hit the ground at the same time, both stones travel the same distance, which is h. Okay, they travel the same distance, h. All right then. Now, what does it mean? Well, it means, so before I move to another page, y1 of capital T has to equal y2 of capital T. Now, because I'm unable to remember things that we've done in the last page, I'm going to have to just do the usual copy and paste job. So let's put all of this together. So we have this, great, don't have to worry about initial conditions. Then what else? Where's y1? Oh yeah, y1 you may have forgotten about. It's all the way over here. Okay, this is y1. Right, now I'm going to rewrite y1 in a second, but just note, for the ease of the calculation, or remember, in order for us to actually calculate something, that we have this condition. And both of these, by the way, at t equals capital T, these displacement functions equal h. All right, so let's come back to this one at the top, y1. So this is displacement for stone 1. Clearly I can do the following. I can add and subtract 1 inside the square. And if I expand this out, so I have g over 2. So if I expand this out, what I would like to have is factors of t minus 1 in the terms that result. So without making a mistake, he says, haha, we get this. Okay, so plus 2 t minus 1 plus 1 square. All right. Now if I just shove this down a second. This is then g t, sorry, g, g, he says t when he writes 2, g over 2, t minus 1 square plus g, t minus 1 plus g. Okay, so I'm going to keep it like that. Now, as you can see, this has a similar structure now, and, well, it's a similar structure to what? It has a similar structure to this now. And you should be able to check if you sub in t equals 0, you should be able to check that this thing satisfies the initial conditions for y1. So let's have a look. Okay, so just a second. What? Okay. So yeah, you can do this, but let's carry on a second. So let's compare the two of them. Now let's get into this. Change the pen. Okay, now we combine these. Okay, so we have the following equation. All right, this is the equation. You know what? That's why. Okay, there's something wrong already. I can hear the screams from home as you watch this. It should be g over 2. So when I multiplied out here, of course, this was correct, but when I multiply 1 by g over 2, of course, I don't get g, I get g over 2. Now, as I said, always double check in manipulations that you arrive at functions that satisfy known properties. So in this case, when when t is 0, we should get, in the first term, we have g over 2. In this term, we'll have minus g. So this is g over 2, minus g, and this is, of course, g over 2. And they combine, clearly, to give you 0, which is what we want. Okay. Apologies for the scrappy calculation. Okay, so let's combine these two. So we have g. This implies we have g over 2, t minus 1 square plus g. Don't forget, it's capital T for consistency. T minus 1 plus g over 2 equals what? Equals g over 2, t minus 1 squared plus 12 t minus 1. Now, immediately, what you can see is this quadratic term just disappears. It disappears, and what you're left with is g times t, capital T minus 1 plus g over 2. And what else? 12 t minus 1. So now you can see I can gather, which is really nice. I can gather things on one side. So I have g over 2. I have the factor with t minus 1 on the left combines with 1 on the right to give me 12 minus g. As you can see, this is messy calculation. Okay, so what about this? Well, this is then t minus 1 equals g over 2, 12 minus g. And then, of course, this is going to give us the following for the capital T. T equals 1 plus g over 12. All right, good. And you can combine these together. And what do we get? So we'll have 24 minus g, 2g plus g minus g over 12 minus g. Okay. Good. So this is our time. As you can see, if g is 9.81, then this thing is positive. Sorry, let me just rewrite this so that it's not so broad in width of pen. And that is a G. It looks like a 9. G. Okay. Looks good now. Now what to do? Well, what I have to do is I have to then now sub, and it doesn't matter, but I can tell you what my initial preference is. Sub t into either y1 or y2 to find h. Of course, if I look at this thing, I immediately throw up because I have to do quite a lot of algebra in this case. So if I look at this one, which is the original y1 that we started with, looks good to me. It looks good to me. So just a point, what I was saying before was this is positive. So if g is 9.81, then of course 24 minus 9.81 is positive, 12 minus 9.81 is positive. So you have some positive number, which is fantastic. I've just realized probably that let's see what happens. Probably the height of this tower is not going to be realistic, but that's not the point. The point was to just calculate some height, knowing the initial data. So I'm, of course, going to go for this one. Why? Because I want an easy life. And what I will have capital T square. And then you just have to do this. Maybe not, actually. Maybe it's okay. Because you get multiplication by g, which is almost 10. Okay. And then you have the square of this guy. Okay, sorry to ramble a bit. That's just some worries of mine in realisticness. So we have g over, now 2 squared in the denominator multiplied by 2 gives you 2 cubed, so 8. And then I have this. Okie dokie. So if you're interested in the height of this tower, that's it. This is h. So if I just budge this up a bit, this is h. And you can go to a calculator. I'm going to go to mine now. And you can program this in. And it gives you hopefully a sensible answer. If not, don't worry, it's not the end of the world. We soldier on, as you know. And okay, so what have we got? It's probably something ridiculous, but let's see. So g divided by 8 times the square of 24 minus g, 12 minus g. In the denominator, square. Okay, not so bad, but I wouldn't say it was the height of the Tower of Pisa. So if you want to calculate this for the person who's interested, it's 51.48 meters to 2 decimal places. You can look up how this compares with the Tower of Pisa. It's probably way off, but actually a long way off, but there you go. That's how it is. All right then. So we're going to go and have a look at one more problem before then looking at projectiles. So see you next time. See you later.